Welcome, ladies and gentlemen. This is what we've all been waiting for. How do you solve an equation with a variable in the exponent when you can't write both of the bases in terms of the same base? That's the problem. So let's consider, I think I posed this question a while ago, or at least a question like it a few videos ago, where I said 2 to the x equals 3. And I said, how would we solve that, right? Or if this was like 2 to the x equals 4, you'd be able to write 4 as 2 squared, or 8 was like 2 to the third, so x would be 3. But if 2 to the x equals 3, I can't break those down into the same base. And it turns out the only way we have to get an x or a variable or anything out of an exponent was using logarithms. So watch how cool this is. It turns out I can actually take the log of both sides, or I'll just log it. Technically, you could even ln both sides if you wanted. The base of the logarithm is actually not significant to us. So we'll have log of 2 to the x equals log of 3. I guess the only reason I might prefer ln is it's one letter less than log, right? Although ln still, I feel weird. I want to write it capital sometimes. But. So now that I've taken the log of both sides, what could I do to solve for x? What can I do with this x here? It's quite the exponent, am I right? That's the best. So what could I do? What can I do with the x? Ideas, ladies, gentlemen, please. Give us ideas.
You move it to the front.
Bam! That's what I'm talking about. Move it to the front. So x times log 2 equals log 3. So how do I solve for x? X multiplied by log 2? How do I? Yeah, divide by log 2. Oh man, I switched over to yellow. Whatever. Just go with it. Divide by log 2, divide by log 2. And I'll get x is equal to whatever log 3 divided by log 2 is. That sounds like a calculator question to me. Blam. So I'll do the old, let's see, log 3, close parentheses for sure, divided by log 2. That one, parentheses are not as necessary, but we might as well end our sentence with a period. And I get 1.5850. 1.5850. 1.5850. And blam, I have solved the equation. And to verify, that means that 2 to that value should equal 3, or, well, more specifically, approximately equal 3. So watch this. If I do 2 to the second answer, all right, so it's going to raise 2 to that power. This should be super close to 3. Actually, in this, the calculator is giving me more digits of accuracy than what I'd written down, and that gives me 3. Whereas if I did 2 to the, 1.5850, I think that would have been, yeah, really, really close to 3, right? Off by a tad, right? So, but that's my point, is it works out. We just solved it. Now, why would that be valuable to us? Why would solving an x and an exponent be valuable to us? Well, I'll tell you, my friends, it's when you want to solve a problem like this, such as how many years would it take to earn, well, I guess earn, maybe I'll just say have. To have, let's say, I don't know, how much money should we want in our account? Kind of like old Kang from that word problem a moment ago. Let's say I want $1 million. All right, that's maybe the not most noble objective, but that's okay. So I want to have $1 million if you invest I don't know, let's say you've got like 10 grand to invest. And let's say we're earning like a good 8.25% interest. And how should it be compounded? What do you guys? Compounded. Let's do monthly or something like that. Monthly. So my question is, how many years? I'm looking for how long it will take for my account to have $1 million in it. All right. So let's define some of our variables. So the ending amount I want is the million. All right. The starting amount that I've got is the 10,000. My rate is 0.0825. And it's compounded monthly, so that's that other variable n. And what would n equal, do you suspect, if it's compounded monthly? 12, yeah, 12 times per year. And because it's compounded monthly, something that's not continuous or not annually, the formula I'm going to use is A equals P times 1 plus R over N, bless you, all to the NT.
What does the N stand for?
The number of times the interest compounds per year. So if it was compounded daily, then N would be 365 and a quarter, technically, if you want to account for leap years within days, or I don't know. That would probably mess things up a little bit. So let's plug in what we know and solve for what we don't, of course. 1 million, 10,000 times 1 plus 0.0825 divided by 12, all to the 12t. So notice my variable is in the exponent. And the only way I can solve this equation, I mean, I guess I could like do a whole lot of guess and check. I mean, I'm guessing I'll have some amount of time to do some guess and check. So theoretically you could. Or I could just use logarithms and just be like a boss and know when I have $1 million. Sounds even better. So one of the things I'm going to do, I'm going to actually simplify a few things at once. Notice instead of distributing this 10,000 into this, because actually I'd have to deal with this exponent somehow first, I'm going to divide both sides by 10,000. And let's see if I can count zeros properly. Actually, maybe I'll just do one of these. So, ching, 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 ching. So looks like I've got 100 on the left. Equals 1 plus 0.0825. Let me do that. 0.0825 divided by, oh, my calculator's not on. 0.0825 divided by 12. And I would have 1.006875 to the 12t. Okay? So that's with the 1 added to it. So this 0.006875, that is the amount of interest earned each month, right? Because I divided the annual interest by months. So I found out how much is being added on per month. And notice that t was measured in years, but by multiplying it by 12, this exponent is now actually representing months. That whole 12 times t is months. T is still years, though. So it basically is figuring out how many times it's compounded over the lifetime of that, earnings or whatever. So what could I do now, do you suspect? Well, I can't just do that willy-nilly. But I could, if I wanted to do that, I could drop the log on both sides. And then I'll be able to move that 12t out front. So 12t times the log of 1.006875. And that's a multiplication sign, not a minus sign there. Right, because I can move that 12t out front using my property of logarithms. Yay, logs. And then to get t by itself, what could I do? I'll divide by a couple things at once. I'll divide by 12, and I'll divide by log of 1.006875. So 12 times log of 1.006875. And that will leave t by itself, which is what I wanted. How much time until I have my money? So I'm going to do log of a hundo. Log of a hundo. Actually, log of 100, we technically could evaluate that pretty quickly. 10 to what power is the hundredth? 2, right? So that's technically 2, but suppose I didn't know that. 12, let's see, 12 times log of 1.006875. There we go. And I hit enter, and I find, what do you know? I find t is equal to 56.0119. And that is the number of years it would take for $10,000 to become $1 million. So at this 8.25% compounded monthly. Right? So if it's actually compounded daily or continuously, it'll actually be a little bit of a larger number than that, is what ends up happening. So if you wanted $1 million 10 years from now, that's what you could do. It wouldn't be bad. 10 grand, put it in the, well, probably, I don't think a bank would give you 8.25%. You probably have to invest in some sort of stock market or portfolio, a diverse arrangement of stocks that overall would limit your risk. What?
That 56.0119, what is that equal to?
This is the number of years. Yep, good point. I should label my answer, and technically I should probably also answer it with a sentence, but yeah, so pretty crazy stuff. So now I know exactly how many years it takes for that to happen. And actually, this technique also can work if you're solving an exponential decay problem. Say you were like carbon dating or something like that, and we're trying to compare carbon 14 to carbon 12, the ratio within like some fossil or something like that, or you'd actually be able to use those ratios and use this logarithmic curve or exponential curve, take log both sides, solve for the time, and figure out how old that thing might be, assuming that those rates have been constant over that time period, of course. So let's take a look at another interesting problem. What if I wanted to solve, this one will be a tricky one, 8 to the 2x minus 5 equals 5 to the x plus 1th power. So, get ready to write a lot of logs. So I can't write both 8 and 5 in terms of the same base, so what do? Log both sides. Right? Solving for x's within exponents, you want to take the log of both sides. And then I'll be able to take the 2x minus 5 and move it out front. So 2x minus 5 times log of 8 equals x plus 1 times log of 5. And notice those parentheses that I was oh so careful about, because the entire 2x minus 5 is being multiplied by log 8. So that means I'd have to distribute in order to properly take care of it. So distribute, 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 distribute. Lots of logs, and I'll have 2x log 8 minus 5 log 8 equals, let's see, x log 5 plus 1 log 5, or just log 5. Now, remember, all of these log things are just numbers, okay? So just think of those as numbers. So I've got some number of x's minus some other number equals some number of x's plus some number. So what I'm going to do is stack my logs into piles. Let's bring the x logs together, and let's bring the non-x logs together. So I'm going to bring this x log 5 over here by subtracting it, minus x log 5. And this does not have an x, so I'm going to want to add 5 log 8. That's not 51 og 8. I don't know why you would think that. 5 log 8. And I'll get 2x log 8 minus x log 5 equals log 5 plus 5 log 8. My goodness. And the expressions on the left both have x's in them. A single x. And it turns out what we can do is yoink, yoink that x out. And we'll only have one x, which is what we want to get by itself. We're so close. X times, well, yeah, 2 log 8 minus log 5 equals this thing. So how could I get x by itself? Divide, right? This big thing is just some number. So let's divide by it. Wimp, 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 wimp. 2 log 8 minus log 5. 2 log 8. Yeah, are you sick of writing logs yet? Minus log 5. So I get x equals this thing, which I'm going to have to plug into a calculator. And I'm going to have to be oh so careful with the parentheses. It'll be like parentheses here and a parentheses here. And also each log gets its own parentheses. So I just want to make sure you're very careful plugging that in. Because it'd be a shame to do all of this work correctly and then just mess up at the very end, wouldn't it? So log 5 plus 5 log 8, close parenthesis, divide, open parenthesis, 2 log 8, close parenthesis, minus log 5, close parenthesis. And I hit enter, and I get x equals, wrong color. How embarrassing. How embarrassing. 4.7095. Meaning, I did a check that I could plug those in there and it'll work out. So 2 times 4.7095 times, double that, minus 5, raise 8 to that power. That should equal 5 to this plus 1. Actually, maybe I'll add 1 to that and figure out what 5 to that would be. It's equal to, this side would equal 9,789, 90 cents. So, well, not cents, but you know what I'm saying. And then, yeah. So good stuff. So we're able to solve for exponents, no matter how crazy or ugly they may be. Well, maybe not no matter, but we at least have given ourselves quite the ability here, which is pretty good. And now, I want to show you something interesting. Well, perhaps. So, you know how your calculator only speaks in 2 log languages, right? It's got like log base 10 and log base E. Turns out there's a way you can communicate to your calculator. Because I know you guys are best friends with your calculators, and like you felt really sad that there's been this like wall between your relationship with it, and like you haven't been able to talk it through. You're like, I just want log base 3 of 5. And your calculator's like, I don't know what you mean. I don't understand you anymore. Oh, it's so sad. But it turns out there is a way to handle that. What if, let's see, let's derive this. What color is a good derivation color? I think yellow in this case. Let's derive a little property. Suppose I have an expression. Let's say I've got, let's see, maybe I could, what if I can pre-plan my variables so it lines up at least, maybe a little bit. Log base, What if I've got a to the n equals b? All right. And if I wanted to solve that for n or something like that, you guys could have, you could take, right, like some log of both sides. But let's suppose I took log base a, bless you, of a to the n. Let's see. Ooh, is this not going to work out the way I want it to? Wait. It's all about the setup here. I know why this is true, but how can I show it effectively? How sad. Well, I'm going to get n equals something. Well, make that log base b at both sides. Let's just see if this works out the way I want it to. Yeah, I think I'm going to mix up the variables of not the way I want them. And I would have log base b of b over here. Yeah, this isn't going to quite work out the way I wanted it to. I should have planned this out better. Blast. Why? Well, anyways, log base b of b is 1. No, I lost it. I lost it, guys. It's okay. I'm going to give this to you, and then let me think. All right, let's scribble this out. There we go. All right, let's look at this formula. So it turns out that log base a of n is equal to log. I've derived this before, but my memory is escaping me. My apologies. Log base b of a is what that is equal to. Log base a of n, log base b. I can't recall the memory. But this is called the change of base formula. Base formula. Where it turns out, I might remember by the end of the video, we'll see. But it turns out that if you wanted to evaluate, like I said a moment ago, log base 2 of 3, that this would equal, notice that both of these log base b's are completely unrelated to the a or the n. I could have log of 3 over log of 2. It would also equal ln of 3 over ln of 2. It would also equal log base, I don't know, pi of 3 over log base pi of 2, right? Pretty much any combination you could take log base of, as long as they're positive numbers, you could end up evaluating what that is. So on my calculator, usually we just use log or ln, but on my calculator, so if I want to calculate that, log of 3, why is it off? Log of 3 divided by log of 2 is what I'd end up getting. And I get 1.5849. Is that? Yeah, 1.5850. That's the thing that I had earlier. That's what I was doing. 1.5850. Aha! Maybe that's my connection. Just trying to remember what it was. So log base 2 of 3. Check this out. That's what I'm trying to remember. Is the same as log base 3, or sorry, log of 3 over log of 2 is what we're saying. And how do I relate it to that? Yes, 2 to the x equals 3. Let's see if I can derive it. So if I had 2 to the x equals 3, I could have taken log 2 of both sides. There it is. Aha! I knew I had it a moment ago. Log 2, log base 2. And I would have gotten x times log base 2 of 2 equals log base 2 of 3. And log base 2 of 2 means 2 to what power is 2. That would be x equals log base 2 of 3. So here we actually have this is equal to that, which is also equal to this. So it turns out that those are equal to each other, is what ends up happening. So that verifies it a little bit for you, that those are the same. But nonetheless, change of base formula. You could now plug in your calculator any base you want as long as you use this division of two separate logs. And it works out quite nicely, And my apologies for the, I'll have to think about that. I'll do that better next time, friends. My apologies. But nonetheless, there's the change of base formula, and I did verify it in the end, at least. So, now you can do pretty much everything with logarithms. Good stuff. Awesomeness. Have a good day, Internet.